Alright guys, in today's video we're going to be covering Euler's method and slope fields. Euler's method is a BC only topic, however slope fields is an AB and BC only, so AB and BC topic. It is a very common topic that you get assessed on slope fields. Euler's method is quite rare. You may see it only in a single part of an FRQ. That's true with slope fields as well, but I just find that slope fields are a bit more common. Euler's method is an approximation technique, a lot like linearization, or kind of like a Riemann sum. We'll go through it. I don't think it's too bad. It's kind of tedious more than conceptually difficult. Let's take a look at this first question where we have dy equals y, and then we have over dx, using the colors on purpose here. We're going to separate the variables. Our goal is to get the y's on one side, so we're going to get the dy and y together on one side. We're going to get the dx. If there was any other x's, we'd want to put them here as well. And we need to make sure that the dy and the dx go in the numerator. So therefore, we would get dy over y equals just 1 dx. Once we've separated the variables, we could take the integral of both sides. To do the integral of both sides, we do the antiderivative. The integral of dy over y is the ln absolute value of y, and the integral of 1 dx is x plus c. Remember, we only need one plus c here, not both, because if you had a plus c on one side, plus c on the other, they can be combined to just make a separate plus c. We're going to solve this equation for y. In order to do that, we'll do e to the power of both sides. So we do e to the power of both sides. Technically, we would have the absolute value of y is equal to absolute value of y is equal to e to the x plus c. However, if we look at e to the x plus c, we recognize that it's always positive. Therefore, y is just equal to e to the x plus c. And using a log property, we can split this up into two parts, which is very common. So you get e to the x times e to the c. That's because if you have addition and an exponent, it's multiplication with the same base. And then you have to consider what is e to the c. E to the c is a constant to a constant. And for the same reason we just talked about, that just turns into another constant. We often call this constant a almost being like an amplitude to remind you of like the other things. You could put a c here, that's totally fine. In either case, you would get this as your solution. Since they give us an initial condition, we can plug this in. So let's go ahead and plug this value in for x and y and solve for c. It's quite a simple one. So when you go ahead and plug it in, you're going to get y of 0 is 1. That means 1 is equal to c e to the 0. Therefore, c is 1. So our solution is simply y equals e to the x. This technique is called separation of variables. Technically, this comes up in the next lesson 8.2, but you kind of already learned it, and you just learned it again here. The main objective, the main tool that you use is you get dy's and y's on one side and dx's and x's on the other, integrate both sides, and solve for y. It's kind of like the opposite of implicit differentiation. If you remember how you did implicit differentiation, you took a derivative and you tried to isolate y prime. Okay, so that's like this warm-up question. We're going to use it later on. So a differential equation is any equation containing derivatives. So it's literally the definition of the two words. Differential means derivative, and equation means equals. So we have those two elements here. And I always like to joke with differential equations that you can call them anything you want. You can kind of call them, and I'll make the text visible here. There you go. You can call them diff EQ, which is very standard for differential equation. Although I like to consider them like diff EQ this way, so you can kind of have some fun with it. There might even be a poster around the room if you want to try to find. I don't know if it's hung up or buried in the closet. Anyway, sometimes I'll call it this one just for funs. Okay, so we have some examples here, which is fine, and then this whole unit really comes down to just these three lessons in a way. There's really one missing, but these are really the three whole big ideas of the unit. And that is, in order to solve a differential equation, we can use analytical techniques, just like the warm-up. It's called an analytical technique because it gives you the exact solution. You can use a graphical technique. That's like my favorite one with the slope fields, where you just draw a bunch of line segments. And finally, we have numerical, which is that new BC only topic, being an estimation technique. So for Euler's method, we can graph the solution with y of 0 being 1. We already did this above, so you don't have to redo it. We got y equals e to the x. So if we have y equals e to the x, we know that this is the solution to this differential equation, and we can then graph it. We know that exponential increase, 0, 1 is on the curve. We know that at 1, we're at a value of e, which is roughly here. We know that as we go backwards, we'd have smaller values, and we have an asymptote that approaches 0, and we have a value here. I'm not sure why I drew that in a dashed line. We have a value going up here, and I'll draw our asymptote in, I don't know, this brown color. So then the question becomes, what is a technique we could use to approximate y of 2 if we're unable to separate the variables and integrate? Effectively, what this is trying to say is pretend we didn't have the solution. Pretend we don't have this answer. But what we do know is just this data. All we know is this data alone. Just using this data. So just using this data, how could we separate y of 2? And the answer is we could solve for y of 2 without separation of variables by kind of doing linearization over and over again. So if you recall linearization, we have y minus y1 equals m x minus x1. This is the equation of a line who has points x1, y1, and a slope of m. Because we're using linearization in calculus, the m comes from the derivative. X1 and Y1 are provided. And if you take a look at what we have in the box, dy dx is y, and y of 0 is 1. We have all the information we need to at least do one linearization. This is x1, y1, and this formula can be used to give us m if we're given the x1 and y1. What that means is we basically have y minus 1 equals 1 times x minus 0. This means that the y is equal to 1 x minus 0 plus 1. So you can kind of convert this in terms of new x, regular y. So these are like your old previous values. And you're trying to convert both of them into their new values, new x and new y. And the way we convert that is just by considering this. The x1 and y1 represent the old x's because those were provided to us. The x1 and y1 were the old x's. So they're here and here, which means they live here and here. If you follow through with all the algebra, you'll see they end up where they are. What we're trying to do is figure out what should our new x be, and based on our new x, what should our new y be. So if you relabel all of these to match down there, what we get is y new equals 1 x new, and that's going to be x old. So we can turn this into a formula to make this a little cleaner. I'm just going to pull up the idea of it over here on my second screen. And we can just kind of make this into some nicer looking things. I'm going to go to this text tool again just to make my life easier. And I'll make the color visible. We'll do y sub new equals m being the derivative, which is really represented by dy dx. So dy dx is m, and then it'd be x new minus x old, and then plus y old. And if we do another step of simplification, we can really make this look a lot nicer. We'll do the exact same equation, but we'll do one last step to it. And that is to make this x new minus x old can be defined as delta x. Delta x times dy dx is just delta y, or the change in y, or dy. So if you really think about it, these are the same. X new minus x old and dx in an estimation technique are the same, so they're going to cancel. And all you're going to be left with is something that doesn't sound very interesting at all. I'll give you a second to look at it, and then you can tell me why this isn't interesting. Y new is equal to dy plus y old. The reason this isn't interesting, dy quite literally just means the change in y. So all it's trying to say is, oh, okay, if I have an old value of y and I need to get a new value, all I do is add the change. So this is kind of a table that you can use. It looks pretty gross, but we can use this table to try to figure it out. And yeah, I was just looking at the example because there's a little bit of the directions are missing. So we're trying to find y of 2, but I think it makes more sense to do, well, we'll do y of 2 here as well. Okay, so the old x is the original one that's provided. That's going to be 0, 1. So we know this is 0 and 1. I'll keep the color theme, so green will be our old values. We're provided 0 and 1. We know dy dx, and we can plug in the values. Once again, we're using this green box here. When we plug in the value of 0, 1, dy dx is 1. Delta x, we get to pick delta x, or it's assigned to us in the problem. One thing that's kind of strange about this problem is delta x is not given. So I'm just going to invent one. Because the next one says with 0.5, I'm just going to start with 1. So we can have the actual last, the next example. So we could say delta x equals 1. Now, if delta x is equal to 1, that's quite a boring example because if we're starting with an x value of 1 and we're trying to get to 2, that's funny that this text isn't quite changing the color. There it is. Delta x is going to be 1 in this problem, and that's going to be the easiest solution because if we're starting at a value of 0 and we're trying to get to 2, it's only going to take us 2 steps. So we're going to make delta x 1. Delta x is a constant throughout the whole problem. So delta x changes, it's constant in the sense that once you pick delta x, you're going to keep making equal sizes. So this number is the same the whole way down. All right, so dy dx is just equal to these two numbers multiplied. So therefore dy is equal to these two numbers multiplied. So that's just 1 again. And then our answer to new x, our new x is the old x plus delta x. So 0 plus 1 makes 1. And our new y is going to be our old y, which is 1, plus the dy, which is 1, to make 2. And now you get to repeat this process. And the whole idea is you take this 1 and this 2 and you put them here and you redo the whole thing, including recalculating dy dx. So all of these elements are going to change, and then you're going to get the next value here in blue, and that's going to go to the next line. And then all of those values will get used to make this, and then you'll get your answer at the end. So this is kind of how it works. It's recursive definition. So if you are familiar with the computer science of this, this is easy to code. It's kind of like a loop or recursion because you're feeding the new values back in and redoing the formula. So let's go through the next iteration. We take 1 and 2 to be our values. Dy dx is once again just equal to y, so therefore it's 2. The total dy is these two numbers multiplied, therefore dy is 2. So it's just 2 times 1. It's coming from here and here, 2 times 1. So this is 2 times 1. I'll show the work on this one too. It's 1 times 1. So therefore it's 2. So then our new x is going to be our old x plus delta x. That makes 2. And then our next value is going to be the old y plus the dy, which is 4. So what is our approximation? Our approximation is 4. Y, oh no, we're not at 2 yet, sorry. We got to do this one more step. What is the value of y of 2? I think we have our value of y of 2. Yeah, we do have our value of y of 2. I was looking at the key. I don't know why they went past this. Y of 2 is approximately 4. Which makes sense, because if you started at 0 and took a delta x of 1, you should only have to do 2 iterations to get to the end. So y of 2 is approximately 4. We know that the answer in reality was e squared. So we can compare our actual to our estimate. I think it's going to be quite off, and that's because we took quite large steps. This is just like Riemann sums in a sense that if you want better answers, you should really consider having a smaller step size. Sorry for the break there. I was just trying to figure out if this makes sense. And this is where it stops. I don't know why the key continues. That is the final answer here. If we're trying to approximate y of 2, that really is where you stop. So I'm just going to put the key goes on here for no reason. So the key that's posted has that mistake, I believe, as far as I can tell. So that's just this line here. But our answer here is 2, 4, which is quite a terrible approximation, which I think is what I was trying to tell you right there. And that's because e squared, which we know is the solution to this differential. We know it's the solution to this differential equation, and that's because it's quite terrible. Here's the actual value of e squared. I'll put it off to the side. The actual value of e squared, 7.389. So quite different than 4. All right. I will do this next one here real quick, just to show you that if you make the step size marginally better from 1 to 0.5, you'll get a lot closer to this actual value, although it's still quite garbage. And then I'll leave you guys to do these next ones if you'd like. I did want to let you know you don't really have to make step sizes of 0.2. Like, this is fun. This is tedious, and you would code this. Like, you won't get assessed on something with a step size of 0.2, like in example 1 here. And then if you look at example 2, this is an example of a non-separable differential equation. So dy dx equals y minus x cannot be separated. So this is where you would learn this in like calculus 4. Your ability to solve this equation comes in calculus 4. Right now you guys are in calculus 1 and 2, so you got some time before you have to worry about this showing up on a test. All right, let's look back at this one. We'll do the same question, the exact same differential equation, exact same initial condition, except we're going to change the step size to be 0.5. Remember that delta x is a constant throughout our problem, and we can set it up from the very beginning as 0.5. We're going to start off with the same initial values. In fact, I'm just going to copy these right here down below to make our life easier, so I don't have to scroll up and down. Here is our differential equation and our initial condition 0, 1. I don't know what I just did. There we go. Okay. All right, there we go. So now we have our initial condition and our dy dx, so we can plug everybody in. We start off with an x1 of 0 and a y1 of 1. dy dx is equal to y, therefore it's 1. And our dy would be the multiplication of these two numbers, so therefore dy is a half. We can use decimals throughout, or yeah, we can just use decimals here. The new x would be equal to the old x plus delta x, so that's going to be 0.5. We know the next delta x after that is 1, then 1.5, and then 2. We know our answer is going to be whatever goes down here in this box. Remember that delta x is the step size between them, so if you're starting at 0, it goes to 0.5, and so on. As a result of that, our new y is the old y, which is 1, plus the dy, which is 0.5, so we get 1.5. We can then use these values to do the next iteration. So we have 0.5 and 1.5. We recalculate dy dx, which is 1.5. Therefore, dy would be equal to 1.5 times 0.5. 3 halves times 1 half is 3 quarters, so that's 0.75. We add dy to the old y, we get 2.25. So now we're at 1, 2.25. dy dx is 2.25. And then we match that up with 0.5 as our delta x again. I'm just going to shift them to be a little more in line. Okay, so now we need to multiply that. That looks like 9/4 times a half. That's 9/8. 9/8 is also 1.125. We add that to the other one, 1.125 times, added to the old y. I believe that's 3.375. Pull up a calculator just to double check. Looks good so far, I think. Yep, and our last iteration will get us home. And in order to do that one, we take these large, lovely decimals, and we recalculate. Dy dx is just equal to y still. And then we multiply these together, and then add them up. So our final dy that we need to add is going to be, and I'm going to switch just to typing this in a calculator real quick. 27 over 8 times 0.5. 1.6875. And if you add that to our original value, we have 5.0625, which you can see we're getting a bit closer. Remember our actual value again, 7.389, and here we are at 5.0625. This is our approximation. So which approximation was closer? Obviously the one with the step size of 0.5. Doing more steps only leads to more accuracy. How can you improve your approximations? Continue picking smaller delta x's. If you pick a very, very small delta x and feed it to a computer, you can get very close. That's kind of what example 1 is having you do. Note that the function is different, so you would have to find the particular solution and compare. I'll let you try these if you want. Definitely use a calculator, though. This is a type of question you would often see in that way, or it'd be provided like number 1, like this example up here where delta x is simple. All right, the second part of this lesson is on slope fields. Slope fields are really, really easy to do. You basically just have a grid that represents slope fields. You have your x and y axes. The dots are all like the scale. The reason why they don't put the scale markers is it would look like the answer to slope fields. So the goal of slope fields is to plug in the coordinates into dy dx and draw the slope at that point. So you plug in the x and y coordinates to dy dx. And I will, once again, make this visible. So you plug in the coordinates. Once you plug in the coordinates, you then draw a line segment with the slope you found. So whatever you get for dy dx represents the slope, so you draw that. For example, let's plug in the values 0 and 0. When you plug in, so here, let's do it this way. We'll do x and y and dy dx. You don't typically have to make a table. I'm just doing it for illustration purposes. Dy dx 0, 0 is 0. We also know that if x is 0 and y is literally anything, it's going to be 0. As well as if y is 0, and this could be anything. Like, you know, all these combinations are going to be 0 because of the product being 0. In either case, the way I like to say that is since we recognize that if x is 0, y is 0, and if y is 0, dy dx is 0, we can just draw a bunch of 0 slopes. The 0 slopes are going to occur if x is equal to 0 or y is equal to 0. This line here represents all the y's that are 0, and this axis here represents all the x's that are 0. When you're drawing your slope field lines, you often just want to draw little segments, like that one's a bit big. And you just want to try to be consistent. 0 is an easy one to be consistent on, but you'll see what I mean later on. Let's go ahead and try this point here. This point here would be represented with the coordinate 1, 1. If we plug in 1, 1, we get 1 times 1 is 1. So that means the slope here would have to be 1. Now, if I'm calling that slope 1, I need to make sure everything's consistent measured to that. If it's steeper than 1, we're looking for it to go up, be closer to this way. And if it's less than 1 but positive, it would be this way, and so forth. Pick another point like 1, 2. We get our answer is 2, so that means the slope is steeper. We pick this point over here. That's 2, 1. The slope is 2, so it should be the same as that one. This point would be 2 times 2 is 4, so we're getting more vertical. Likewise, down here, we're doing the same thing, except now one of the x's, the y's are all negative, meaning the slope is negative, so this would be a -1 slope. This would be a -2 slope. This is a -2 slope, and this is a -4 slope. The logic of this is going to repeat, and the only difference is whether it's positive or negative. In quadrant 2, it is also negative. So we have -1, we have -4, we have -2, and -2. And I just want to make this one look a little nicer. All right, same thing down here, except now it's positive again. So this would be a slope of +1. This would be +4. These would be +2s, +2s. It's okay if it's not perfectly the same as you did up there, but as long as you're getting close to the values you want, it should be pretty good. That's how you generate a slope field. A slope field represents a potential of all different solutions. So you know that when you integrate a function, you often get plus c. The slope field represents how the plus c may impact the rest of the shape. In a standard function, in a normal non-differential equation context, you can kind of see that one here with x squared, what it really looks like. So we know what the integral of dy dx as x squared is. Dy equals x squared dx would be the first step. Then we integrate both sides. When you integrate both sides, we're going to get y equals 1/3 x cubed plus c. And then take a look at this picture. What does this picture look like? Well, if you drew a dot, say you picked any one point, it tells us to pick the solution through 1, 1. So here's 1, 1. What do the solutions look like if they live here? Well, the slope here is going to be the same as the slope pictured. So the slope is going off to the right, then it's going to be getting steeper and steeper and steeper. And if you go to the left, it looks like the slope is getting flatter and flatter. Then it gets completely flat, then it goes down and goes very steep. The goal when you're drawing these is kind of not to like follow exactly the lines. You're not like connecting the exact lines together, but you're just kind of following the pattern. So the slope field just generates a visual representation of all the various versions of what plus c looks like. Note that this symmetry you see is true in the event that you have just a dy dx as a function of x. That means that there's no y dependence. If there's no y dependence, then there's no y dependence in the slope field. Notice how all of these have the same exact slope. That's because as y is changing, dy dx is not changing. Y is irrelevant. Y doesn't matter. In all of these highlighted sections, x is equal to -2. If x is equal to -2, then when you square it, x is equal to 4. The y values are irrelevant, and that's why you see this happening. That's going to be different than if you look at this example on the left. If you look at the example on the left, it's kind of the example we just sketched, just made bigger and prettier. You'll notice that they didn't really draw in the zero slopes here, though they could have. And you'll see that we get different behavior depending on where you are. For example, the solution that goes through 1, 1 is this one. It looks like it goes off to the right this way maybe. And then it gets kind of flat and goes off to the left this way. When you're following the slope fields, you'll notice we don't even get to the bottom part, and that kind of deals with that asymptotic-like behavior as we get near 0. So slope fields are kind of nice. It's a family of solutions, and it just illustrates your solution once you get a starting point. Sometimes you have to go backwards, and you can use some of my tricks. One of my tricks is look for patterns, look for zeros, and then find out which one would produce that 0. Another trick is look for x and y dependencies. So if you look for, you can look for patterns. What are the patterns that you could look for in no particular order? Patterns that are helpful are trying to find where things are 0, meaning like, do you see any slopes of 0? So look for slopes of 0. Ask yourself, is it x dependent? Question mark. Is it y dependent? Question mark. If you can answer these questions, you can really narrow it down. If the answer depends on x, then there's an x in, then dy dx has an x in it. And if the answer depends on y, then dy dx has a y in it. If it depends on both, then it has both x and y in it. So let's go ahead and just look at what we got based on these. These are generic rules that work all the time when you're looking for patterns. Sometimes the patterns you find aren't necessarily the most helpful, but these are kind of some rules to look for. So let's look for all of these properties. First off, do we have any slopes of 0? Sure we do. They are here. Do you notice a pattern in what slopes are 0? If you graphed this line, where would it be? What is this highlighted blue line? If you just connected those dots, that would be the line y equals -x. That means when y equals -x, dy dx is 0. Based on that, you can already figure out which one of these is correct. If y is equal to -x, then they should sum to 0. So x minus y would be x minus -x. That's not going to be 0. Instead, it's going to be something like x plus y. So there's going to be our answer here, and we're done because we did one pattern. We can also take a look at the other two questions just so you see what it's like. Do our answers depend on x? The way you tell is highlight a single row and ask yourself, are they changing? Yes, this row is definitely changing. The way you ask yourself if it depends on y, you highlight a single column and you ask yourself, are they changing? Yes, these are definitely changing. So we know our answer has x and y in it. If you want to be extra sure, take a point that you found was 0, such as negative 4, 4, plug it into here. Negative 4 plus 4 is 0. Yay. You'll see that none of them produce 0 if you plug in negative 4 for x and 4 for y. They just don't quite get there. You could apply those techniques here. These will kind of help you out. And then this FRQ down here is kind of the same idea. You get to see it live in action. You're provided the slope field and asked to sketch a solution through the point 0, negative 1. That's this point down here. B says use Euler's method with a step size of 0.1 to approximate 0.2. You'll see that this kind of proves my point that they don't give you miserable questions. You're using a step size of 0.1 to get to 0.2 starting at 0. 2 iterations only. Not so bad. It tells you this is a solution. Justify your answer. So you're just going to plug this guy into the derivative and solve. And finally, G is a solution and it has an extreme at 0, 0. Is this point a local max or min? So it's telling you G is some solution. You don't have to solve for it. It gives you G of 0, 0. And it asks, does it have an extrema at the point 0, 0? So you'd plug in 0, 0 and tell me what happens to dy dx. So dy dx at 0, 0 is 0, which is good. That's a chance that it's an extrema. And then how do we know if it's a local max or min? Well, we'd have to use like the sign chart. We can't really make a sign chart because we have no idea what the function's doing. So instead, what we do is the second derivative test. So use the second derivative test to answer part D. All right, well, that is the overview lesson for Euler's method and slope fields. We will definitely go over some of these when I get back, but hopefully this helped. Have a good one, guys.